we have the reaction like this. A decomposed to be B, and this reaction occurred in the batch reactor. This reaction is the first order reaction, and it is found that 65% of reactant A decomposes to produce uh, B within 30 seconds. Find the fraction of reactant A which is still remain in the reactor after we let the reactant stay inside the reactor for 1 minute. So from this we got to set up the equation. We know that if we say that the reaction occurred as the first order, that means right? A is the reactant. By the time passed, the concentration of A is going down, right? Because it is the reactant. So I said dCA means the difference of concentration of A when the time passed. It would be negative number, right? Right? Because it's going down by the time passed. It's turning to be the product. And this rate is vary with the concentration of A. The first order it means it is vary with the concentration of the reactant. In this case, it's A. So when we set up the equation, we would get something like this. Okay, and then they said that here let me draw the batch reactor. The way that batch reactor works is just that you put the reactant into the reactor once, and then you just let the reaction occur inside the reactor by time. If you put it longer time, reactant A would change to product B more and more, right? The meaning of that means that. So from this, you always know how much of reactant A that you put into the reactor at the beginning. So I said in the beginning, it means at T equal to 0. I said that Ca is equal to Ca0. 0, 0 is mean the initial concentration of reactant A. Okay. And at T is equal to any T, I said Ca is equal to any Ca. And this Ca is always smaller number than Ca0. Right? Because Ca0 is its initial concentration that you put in there at the beginning. By the time passed, A is converted into B. So the concentration of A is going down by time. Okay? So now this equation is the first order differential equation. It is a separable equation. So the way that we do, we would get to find the answer. K is the rate constant. It's the constant number. So you do integral and then you put the boundary condition for both sides. You would get at the beginning, you get A0 and this is Ca, 0 and T. K is a constant, you can take it out. Integral dt equal to T. So you would get Kt there. And integral negative 1 over Ca dCa, what you get? Minus ln Ca. And then you put boundary condition there. Plus the boundary condition, you will get something like this. Or you can rewrite it again to be this term. The problem statement saying that we want to know the fraction. Fraction is CA over to CA0. It means fraction already, right? Fraction of reactant A, which is still remain in the reactor after 1 minute. You know time, 1 minute. But you can't find the answer because you don't know what is the K. But before they asking you to find the fraction, this is the main idea that the problem statement gives to you. What is the significance of this? It's saying that reactant A, 65% of reactant A decomposes to produce to the product within 30 seconds. You know here, you know T here. You don't know CA. CA is whatever remains in the reactor. But they're saying that A decompose, 65% decompose. So how many remain? How much of A that remain in the reactor? 25%. So that means you know the fraction of CA over CA0 equal to 0.25, right? 0.35, 0.35, 35%. From this, you can find K, okay? So we can say that K is equal to 0.035 per second, right? The unit is 1/second. This term has no unit, right? Because CA and CA0, they are the concentration. You divided them, so this term got no unit. So now the unit of K just go by the time. So finally we would get the unit of K per second.